In this video, we're going to be taking a look at 4.2 ratios within similar triangles. Okay, so in the previous video, we looked at parallelograms. Now we are going to be looking at triangles. All right, everything is very much the same. The only difference is, again, we're looking at triangles. Now, since rectangles have four 90-degree angles, you can show that rectangles are similar by comparing side length, which is what we did, like adjacent side lengths. All right, so here you have two people. Junique explains that all scale factors between corresponding side lengths are equal for similar rectangles, which is true. All right. So he compared this one to this one, and then this one to this one. As you can see in those ratios down below, the scale factor is 1.5, meaning this is 1.5 times larger. Okay. So Curtis down here says, hey, rectangles are similar if the ratios of corresponding adjacent sides, which is what we did in 4.1. So here he's comparing then this one to this one and this one to this one, 9 to 4.5, and notices, hey, these are equivalent. If you put those in a calculator, simplify them all the way down, they are equivalent to each other. Okay, now this one only works because it's rectangles. Doesn't always work. Like we saw with parallelograms, it doesn't always work depending on the angle. But in a rectangle, since the angles are always 90 degrees, they will always be the same. So you just need to be careful with triangles. That comes into play here, right? You have to be careful with the angle measures. So taking into account everything we know, go ahead and try to figure out which triangles are going to be similar to each other. All right. And you can use, I believe, there is a lab sheet. Yep, that looks like this. So you can write on it. Just remember everything that needs to be true for them to be similar to each other as you figure this out. Go ahead and pause the video, try this on your own, and then come back and see how you did. All right, so let's take a look at this. First of all, what I did is I went ahead and figured out the missing angle. So some of those angles that were missing were 89, 30, that one was 61, and that one was 75. Because remember, every triangle needs to have 180 degrees in it. So just figuring out that missing angle is pretty simple. Now, understanding that all angles in similar triangles need to be equal, one of these we can automatically throw out, and that would be triangle B. Okay, and we can throw that out because look at the angles. 42, 75, 63, that's different than 61, 30, 89 for all of the other ones. So bye-bye triangle B. Now let's look at the comparisons of corresponding side lengths. So for example, for triangle A, let's compare the smallest to the largest. Okay, so that would be, I highlighted all of the corresponding sides, so you can see all the the red, pinkish ones are the smallest. So I'm going to write all of the smallest. So that's 4, 6, and 10. And let's compare it to the largest. And I highlighted the largest like that orange yellow color. So that would be 8, 12, and 20. Now let's look at these ratios. You notice they all simplify down to 1/2, meaning they are all similar to each other. Now that's not a scale factor. Doesn't make sense. There's 3 different sizes. There's different scale factors for each one. That's just if you have multiple shapes to figure out if they're similar, this is an easier way to do that, because if we did scale factors, we'd have to compare this one to this one, this one to this one, this one to this one, right? So if we don't want to do scale factor, this is just a smarter way around that. Okay, so we know that triangles A, triangle B, triangle D are similar because same angles, and then the length of the corresponding sides are all similar as well, or they're the same. And you can compare any of them. Let's go largest to middle. So 8 to 7, 12 to 10.5, and 20 to 17.5. Now, if you find what all of that equals, which I'll find for you here, 1.14, and it goes on, but all of these actually are going to be 1.14. And that's just, all of those are going to be the same. You notice it's different 1/2, but if you compare corresponding sides on the triangles, adjacent sides on the triangles, the same ones, then you get the same ratio. Now we've answered part A. Hopefully you can explain your reasoning. Go ahead and pause the video and do that if you haven't already. Part B, number 1, within each triangle, find the ratio of the shortest to the longest. We already did that. Find the ratio of the shortest to the middle. We did long to middle. So if you did that with us, long to middle, that's fine. You don't have to do that. What do you notice about the ratios in part 1 for similar triangles? Well, hey, listen. All of them were the same. The ratios were the same. And for non-similar triangles, we didn't even look at this one because we already knew that that one wasn't going to work. But if they were non-similar, the ratio would have been different. It would not have been 1/2 or 1.14. It would have been different. C, choose two similar triangles, find the scale factor from the smaller triangle to the larger. What information does the scale factor give? Go ahead and answer part C on your own. Pause the video, answer it, and then come back. So let's look at triangles C to D, small to big, right? So 12 to 20. So if I'm comparing these, 12 to 20. I'm going to go, because if I want to go small to big, I'm going to actually put the big one on in the numerator. So 20 over 12, let's see, 4 goes into both of those. So 4 goes into 25 times, 4 goes into 12 3 times. And so this triangle right here is 1 2/3, 1 2/3 times larger. That's what that scale factor will tell you. So if I compare this one to this one as well, I will get 1 2/3. If you do 12 to 8, right? This side to this side. And I want to use those yellow highlighted sides because those are corresponding sides. That is also 1 2/3. Okay? I'm sorry, it's not. Sorry, scale factors are not always the same. This scale factor is going to be a little bit different. But if you compare all of the side lengths from triangle A to triangle B or C, the corresponding side length, they're all going to be 12 over 8, which, let's see, 4 goes into 12 3 times. This is going to be 1 1/2. So triangle C is 1 1/2 times larger. And then C in triangle D is 1 2/3. So even though these ratios are different, right, it doesn't tell us about all three of them, whether all three of them are similar, like the ratios that we did previously. It just says between these two, are they similar or are they not? How much bigger or smaller is one triangle than the other? So make sure you answer part C. What does the scale factor give? It tells you how much bigger or smaller that triangle is. And D, compare the information given by the ratio of side length in question B and the information given by scale factor in question C. We've also talked about this multiple times. The ratio of the side lengths, that doesn't tell you anything about the comparison of the shapes other than the fact that if the ratios are the same on all of them, then they are similar if their angles are the same, okay? But the scale factor, okay, the scale factor takes more work because you have to check multiple sides to ensure just from one figure to another. You can't compare a page of shapes. You can only compare two. So with the scale factor, you have to do more work, but it tells you how much larger or smaller one shape is than another. And in order to determine if they're similar, you have to check all corresponding sides. So for a triangle, you would check the 3 corresponding sides to make sure those 3 ratios are equivalent. Because if they're not, then it's not similar. Okay, that is it for 4.2. Ratios within similar triangles, very similar to 4.1. The difference is the angles for triangles. If they're different, they are not similar. Same with parallelograms. Rectangles, they're defined as all the angles are always 90 degrees, so that's a little bit different.